Okay, here we go. The pegboard. So this week's lab, this is the pre-lab for the pegboard lab. We're going to implement this exciting pegboard lab. Woohoo! This thrilling pegboard game. Watch this. Look at how good I am at this. We're not going to implement it with the fancy GUI. In fact, our GUI will probably just be text. But we're going to implement the underlying mechanics of the game and plug it into an artificial intelligence framework that will then allow us to solve the game. So that's our plan. And so, just as a review, to formalize any puzzle, in other words, to formalize a one-player game in artificial intelligence, you need an action function, so a way to get a list of legal moves for a given state, a results function, which given a state and a move, you can apply that move or action to the new state. I should mention that the word move and the word action are used more or less interchangeably when talking about puzzles. So if I use one instead of the other, that's what I mean. You need a goal test to let us know, is this the goal state? There's also the possibility of a state cost function, but we actually don't care about the state cost function because all of the costs are uniform. In other words, jumping a peg is just as good as jumping any other peg. For 8 puzzle, moving pieces around is just as good as moving any other pieces around. We don't really care. Now we're going to be implementing this in Java. If you notice up here, solving puzzles, we're talking about action function, results function, goal test function. We're talking about functions. Of course, in Java, you actually can't pass functions around because Java is object-oriented. Instead, we're going to write classes that implement interfaces. These are what are called functors, and that's what we're going to do. Now, this artificial intelligence, a modern approach, or AIMA, it has a framework that actually will do all of the graph traversal stuff for you. It's got A star, it's got breadth first search, depth limited search, iterative deepening, branch and bound. It's got all these different varieties of searching, but they're all basically some version of like depth first search, other than breadth first search. And you don't actually have to write any of that code for you. You could build it out of your graph lab, but it'd be a lot of work. So we're just going to use a framework that does it. We're going to focus on the state. Now this framework itself, it's actually in a library that's already going to be included with your Eclipse project. So I'm going to give you an Eclipse project that looks something like this. It probably won't be called CS317 8 puzzle. I'll probably rename it 262. You can tell we used this in CS317 a couple years ago. You'll have this simple 8 puzzle package. You probably won't have these other packages. Now if you notice in here, reference libraries, it's got these AIMA things. And then here in lib, it's actually got the jar files and, I don't know, a zip file which probably has all the source and stuff like that. So I've already configured Eclipse. This is sort of like a class path if you remember from your days of command line Java, if you had days of command line Java. Eclipse manages all the class path stuff for you automatically. And that has all the code that'll do the solving in there for you. So let's talk a little bit about the 8 puzzle board, which is a example class. It's actually the state for the 8 puzzle. And the methods we particularly care about, constructor, moving gaps down, left, right, up, and checking if you can move a gap. And then I'll show you how the action function, goal state function, results function actually work. Crap, let me just check my calendar real fast. Oh my god, that's the advertisement that the pegboard game loaded. I got 10 minutes until my next paper conference. Okay, great. Let's see if I can get through this. So this 8 puzzle Eclipse project, has been, I guess I have that slide in there twice, that's been provided as an example. Let me go ahead and show you kind of what this looks like. So these are the action function, goal test function, result function. They're really functors. I'll show you those. This is the driver that drives all the code. But before we get to that, I want to show you the 8 puzzle board. That's this class here. It's got some static variables to represent the different moves, left, right, up, and down. These dynamic actions, if you hover over this and bring up the documentation, you'll notice that these are things that are coming out of the solving framework. For 8 puzzle, this makes sense. Really, if you think about a move, an action in the 8 puzzle, it's all about moving the blank up, down, left, or right. For a pegboard, that's probably not going to work. Because you need to know not only what direction, and there's 6 possible directions, you also need to know which peg. I can't just tell the pegboard, jump left. Which peg should jump left? There might be two legal left jumps. The state we're actually just representing for the 8 puzzle, just an array of ints. You could do it as a 2-dimensional array, but we kind of know what the 8 puzzle board looks like. So we're initially starting out with everything in order. We got a shuffle tiles method. That's not that exciting. This is just making a bunch of random moves to get the board shuffled up. What we're interested in is move gap, up, down, left, and right, and can move gap, up, down, left, or right. So you notice we've got these actions. What is action? Well, this, if we sort of open up the source for it, this is an interface that comes with the class, the Artificial Intelligence and Modern Approach Framework. And it's really just a marker interface. It has this isNoOp method. We're just going to return false in that because it's totally irrelevant. We never end up using it. So this has got this move, and what it's doing is it's just checking, well, is the move left, right, up, or down? And then if it's left, it's making sure that the y coordinate is not, 0 or 2, because you can't move left if your y coordinate is 0. You can sort of look at these methods to kind of try to figure out more of what they're doing. If we sort of look at get y coordinate, it's like saying, okay, well, if we mod by 3, that tells us the y coordinate, and then the x coordinate we just sort of divide by 3. This is a product of just using a 1-dimensional array to simulate a 2-dimensional array. You can kind of figure out, okay, position 0, 1, and 2 are the first row, which means the y coordinate would be 0, and the x coordinate 0, 1, or 2. 3, 4, 5, that's the second row. Well, 3 divided by 3 is 1, 4 divided by 3 is 1, and 5 divided by 3 is 1 because it's integer division. Similarly with mod, that's telling you what column you're in. So that's basically what's going on. So this is just doing all these things to check that. Now the left, right, up, and down, what does that mean? Well, these things here, these are basically singletons. So we're creating a left, right, up, and down. Dynamic action, if we open up F4 does this. It's a little bit slow. Come on. There we go. The type hierarchy, you'll see that that's not what I expected to see at all. Huh. I expected this to implement action. Apparently it does not. Doesn't that suck? Huh. How is that possible? Oh. Action is not a class, it's an interface. This is the class hierarchy. If we look at dynamic action, so sort of open this up, you'll see this extends object with dynamic attributes. No, that's not what I meant. Damn it. If we open this up, you'll see that this doesn't do at all what I thought it did. God damn it, I'm going to have to record this again if I can't get this to look like what I want it to look like. Oh my god, doesn't that suck? How are they passing an action without something actually frickin' implementing action? Somebody, there we go. Gah, it's right here. I should have seen this before. So dynamic action implements action, right? Which is how we're able to have actually just sort of like pass in an action and then check to see which of these actions it is. And so that's checking if we can move the gap up, down, left, or right, and it's figuring out, well, is it in a row or a column where this would be a legal move? That's what's going on there. Now, other things we care about are these are sort of the methods that actually do these moves. So if we look at, like, can move up, down, left, and right, now the difference actually sort of to move things down, well, we figure out the gap position, the x and y coordinates, we check to make sure that the move would be legal. Then we actually kind of do the move and actually update the state. And we do that, we have that possibility for, up, down, left, or right. We can go ahead and kind of do this. Now there's a whole bunch of other methods in here because when they wrote this class, they apparently went crazy and wrote just tons of different things for it. The only other method we really, but these methods, these are basically methods that your result function has to call. Right, these are what actually do things. This one here, this is figuring out, well, what moves are possible. So you could use this to figure out what all the possible moves are. And then finally, you've got your toString method. This actually returns the state as a string. So it's sort of like state 0, 1, and 2 with some spaces in between, then a new line, then 3, 4, 5 with a new line, then 6, 7, 8 with a new line. The beauty of this toString method, this displays the board. It doesn't do it with a fancy GUI, it just does it in text, but it's good enough to test your program. Being able to test your program without having to write all of the GUI stuff is one of the most incredibly important and profound things in computer science. It's called Model View Controller. Sorry, I'm recording. Okay, so let's see, other things that we can do. Okay, so the interfaces for the key functions, we've got action interface, result function, and the sort of goal state function. These are all interfaces. The action interface is really just a marker interface. It has to have this Boolean is no op. If you look at the way this is implemented, the actions function, we've got our implementation. We don't actually really... Oh, it implements actions function. God damn it, why do they make everything so complicated? That bites. I'm going to have to re-record this probably. Well, we'll see if we can keep going. So this implements actions function, which is a type of action. And what it's going to do, it has this actions method, which has to return a set of possible actions. And so we're going to sort of take the state. We assume it's an 8-board puzzle. We're going to go ahead and downcast it. Then we're going to create this set of actions. And then we're going to go ahead and ask the board, can you move up? Can you move down? Can you move left? And if it can do any of those things, we're going to add those actions to the set and then just return it. And so this little class, it queries the board and says, hey, are these moves legal? And then it returns a set of those moves. Now another way to do this would be to sort of like put a method that returns a set of actions inside the board and then just have this actions function call that method. That would also work. Goal test, this is actually really easy. This is what we'd like the board to look like. So the goal test just says, okay, take the state we've been passed, downcast it to a board, and if the board equals the goal that we're looking for, return true. So return the result of this comparison. This comparison will be true if it's the goal state, false otherwise. That's a really easy goal test. The result function, this is pretty simple. It's a result function. That's the method that we're inheriting from this result function interface. Given a state and an action, we want to apply this action to this state. So we're going to take the state, downcast it. These are all written to work with object. We actually can't make these generic because we don't really know what type anything is. So we're just going to rely on downcast. It's a little bit sloppy, but it works fine. And that's how the framework's written, so we're sort of stuck with it. So, you know, if this action is the up action and we can move up, go ahead and make the move up. Now, you notice we're actually making a copy. This is a copy constructor. We're copying the 8-puzzle board, then we're moving the new board up and returning the copy. We're not actually taking S, sort of downcast to board, and then changing that. The reason for that, you imagine we're building out a big tree. We need to have a separate state for each node of the tree, right? Because each state might have multiple possible moves from it. Well, if you take that first possible move and sort of change the original state, you've then lost that original state. So we have to create and return copies in all of these methods to actually get this to work. So basically you implement 8-puzzle board, you implement the game, you have some representation of the actions, what the moves look like, and then you go ahead and start applying moves to it. And that's what this does, and it has a toString method and everything's really lovely. These three things, this is just what makes the solving framework work. So if we look at the solving framework, we're going to, random number generator, we create the puzzle board, we shuffle it. You obviously don't have to shuffle the pegboard. You sort of just create it. We create our actions function, we create our result function, we create our goal test. We create an instance of problem with the initial state, the action function, the result function, and the goal test. This constructor, if you look at the documentation of this constructor, oh my god, that's slow. Oh, there we go. You'll see it still expects the initial state to be an object because once again it doesn't really know the type, but these other things, it expects an actions function, result function, and a goal test. We create the kind of search we want to do. In this case, depth first search. We're created out of a graph search. This stuff you're just going to mostly be basically all this stuff you can kind of like copy paste. We create a search agent out of the problem and the type of search we want to do. We get the list of actions. I'm just going to go ahead and print them out because that'll be nice. Oh wait, no, I'm sorry. The act of creating the search agent actually solves the game. And then when we ask the agent, well, what are the actions? It'll tell you, well, here are the actions you needed to solve this puzzle. And then we're going to go ahead and print out instrumentation. This is like how many nodes did it explore and stuff like that. And so once again, the brilliance of this, you create your initial state and your actions function, results function, goal test, and then all of this code down here, this just goes ahead and solves the puzzle, assuming that you have told it these 3 pieces of information. And of course, what's fantastic is you can actually solve any puzzle this way, or at least run this framework on anything. It's not clear that you can actually solve the puzzle because some of them are too big to solve in memory. Okay, I'm going to stop. I may re-record this. We'll see.